Last year you learned about the topic of dynamics. And the key idea from that was that when the net force acting on an object is zero, the object will move at a constant velocity or have uniform motion. However, if the net force was not zero, it means the object will accelerate. So the next two topics, this one's on equilibrium, next one's on dynamics. So equilibrium is when our net force is zero. So there are two conditions that must be satisfied for static equilibrium. So in other words, we're saying for things to not move, because if things to not accelerate, because again, if the net force is not zero, things will accelerate. So our first one, translational equilibrium, our vector sum of all forces acting on a body must be zero. Next day we'll look at something called rotational equilibrium, and this is the sum of the torques acting on a body must be zero. So translational equilibrium describes motion as like sliding motion or pushing. Like if you were to push something, it's going to move across the floor, or if you're going to lift something, it's going straight up and down. Torques describes rotation. So imagine if you had like a wrench and a nut. If you apply a force on the wrench, it'll cause the nut to rotate. And we call that a torque. We'll get into that more next day. So the key idea for solving any dynamics problem are free body diagrams. So this is an example of a free body diagram, so we don't forget how they work. So if I have some object, a free body diagram shows all the individual forces acting on that object. So for example, I might have some force over here. I might have a force acting on it in this direction. I might have a force downwards, like gravity. So F1, F2, F3. Okay, so it shows all the different forces acting on a body. And for a tip-to-tail diagram for forces, one way of knowing if the vector sum of all forces acting on the body is zero is that if, when I add up those three vectors, like F1 and F2 and F3, if the beginning and end meet up, that means I know the net force is actually zero. So F1, F2, F3. Again, remember from tip to tail method and vector addition, order does not matter. I could have done F3 and then F2, then F1. It still would end up the same. I can do F2, F3, F1. It doesn't really matter whichever direction. So although different forces may act on an object in static equilibrium, the net force it experiences will be zero. We define this to be, here's our first one. This is the mathematical symbol for sum. The sum of the forces is equal to zero. Or this means the sum of. And that's to end it, just for two-dimensional equilibrium. So we said that the sum of the forces must equal to zero. However, we can be more specific. It's just like we saw for vectors. Any two-dimensional vector can be separated into its x and y components. So more specifically, we're going to say the sum of the forces in the x direction must equal to zero, and the sum of the forces in the y direction must equal to zero. Now we can add units for forces than Newton if we want. There we go.